أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم ألف لام ميم تنزيل الكتاب لا ريب فيه من رب العالمين أم يقولون افتراه بل هو الحق من ربك لتنذر قوما ما أتاهم من نذير من قبلك لعلهم يهتدون الله الذي خلق السماوات والأرض وما بينهما في 6 أيام ثم استوى على العرش ما لكم من دونه من ولي ولا شفيع أفلا تتذكرون صدق الله العظيم. अल्लाह ताला फरमाते हैं कि अल्लाह ताला ने सारी कायनात तन्हा बनाई, कोई उनका शरीक नहीं और हमारा कोई दूसरा दोस्त और कोई मददगार भी नहीं. तुम क्यों नहीं समझते हो बात को? यानी ये जो हमारे आसरे नज़र आते हैं दुनिया में, ये सब एक धोखा है. एक ही हमारा आसरा है, सहारा है, वो है अल्लाह ताला की ज़ात. ये समझ ले इंसान तो दुनिया बदल जाए. So today we will just review things that we have been doing, and I will try to explain why we do these things. And one thing that is important to understand is that this is not at all the conventional understanding of what data analysis is about, but the conventional understanding is very wrong, very deficient, and cause for many difficulties. So let me just review what we have been doing. We're just going to do the whole thing over again from scratch. So we start with the panel data. Now panel data is especially suitable for Bayesian analysis for reasons that I will explain later. Normal single time series is not very suitable, and Bayesian doesn't work very well over there. In some special cases it can, but the real place where Bayesian shines and where it has not been used very much because people don't understand this is the panel data situation. So what is panel data now? Once I describe it as XIT, I goes from 1 to n, t goes from n to t. But now having worked with real data, you understand what this means. The symbols have a interpretation. So the I is labeling the countries, and the t is labeling the time, and so we have a panel of data. And the panel should be concrete and visually observable. I mean, when you mention these symbols, the picture of the real Excel spreadsheet should come before your mind, so that, see, at all points one has to work with the abstraction and the concrete, physical, real world representation. At the same time, you have to keep both things in your mind. If you just have a square of numbers in front of you, you will not be able to understand how to systematically work with that. So you have to have the symbol XIT. But if you just work with the symbols, then you won't know how to use it in real world. So both of these things, that XIT is your symbol, and then what it means, it's the value of the money to GNP ratio in the ith country at t period of time. So this is something which most people don't learn. So that's why things like this happen, that somebody has learned statistics, but he doesn't know how to compute the average of 10 real numbers, because he has learned the formula for the average is 1 over n summation I equals 1 to xi, but he doesn't know what it means in real life. Alright, so of course when you look at the country and time, this is not necessarily the only thing. There are many other interpretations which can be used. And okay, so to start data analysis, we assume that these things are IID with some that for each country the observation is IID with common mean and variance, which doesn't depend on the time index. So this is a strong assumption. It means that things are not changing across time. This is sometimes called stationarity. Stationarity means that the distribution of the data is independent of time. As you shift across time, the distributions don't change. So we have assumed that that is true, and that's something you can check visually, and we will do that now later when we go to real data analysis. So in particular, data should not contain time trends. If you inspect the data and it has time trends, then you should not use this analysis because it is making a false assumption. Often you can apply a transformation to the data to achieve stationarity. There are different kinds of data which are useful in different contexts. Sometimes what I did was I just chose a small period of time where the means did not seem to be changing, and also the variances did not seem to be changing very much. So that was one simple way. But suppose I want to deal with the whole data set. Then if you have a trend, normally you can eliminate trends by differencing. So you look at first differences of the data, and there are other ways also. Actually, how you eliminate stationarity is depends on what is the underlying real world structure of the data. You should have some interpretation for what you get after you eliminate the trend. It should be something meaningful. So for example, one way to take differences is to take the log of the log GNP minus log GNP minus 1, which is the log of the ratios. So that's a logarithm of a growth rate basically. So the variable that we are analyzing is the rate of growth of GNP. So you should always, when you make a transformation, have an understanding of what that transformation is doing. So one assumption for the IID is that they are the same across time, and the second assumption is that they are independent. Again, there are visual checks for independence, which we will see how to do later. And there are also formal tests for independence. One simple way is to take the lag of the series by one period and run a correlation, and then test the correlation for significance, because the correlation will never be actually exactly zero, which is the independence case, but it will be, maybe it will just only a little bit different from zero. So you have to check, is there a significant correlation between the series and its lag? If it's significant, then you reject the null hypothesis of independence. If it is not significant, it means that there is a correlation, but it is due to random fluctuation. It's not genuine. Okay, so this is preliminary before data analysis. Now, one thing that is crucial that is not understood or stated in books is that the object of data analysis is to find IID structures in the data. And these IID structures should be plausible. That is, intuitively, it should be understood that, well, for example, when you're saying that the GNP is not IID, that makes perfect sense because the GNP is growing, and so and we expect it to grow, so we don't expect it to be IID. If I say that the growth rate is IID, it means that the growth varies randomly, fluctuates from time to time, and the fluctuation is about the same in each period. Now this is what it means. So is this true? Well, maybe not. Maybe there are some periods in which there are growth spurts, and so growth speeds up, and there are periods in which growth is in doldrums. So even though it's random and it fluctuates quite a bit, and also the growth rate of this year is independent of the growth rate of previous year. These things seem plausible, but to think that they are the same distribution all over time, that doesn't seem very plausible. So you have to try to find a data set for which either the assumption is plausible, or if it is not, then you adjust the analysis to take care of this. So you say, okay, 90s was a period in which growth was slow, so we set some parameter to show slow growth, and then maybe 70s was a high growth period. So you can adjust the data analysis to take care of things like that. But for the moment, we are thinking of the simplest case, where we have an IID structure. The thing is, you can't impose the structure by assumption on the data. And this is what is the most common practice in econometrics, that you just assume that something is IID and then you start analysis without bothering to check. There are two things to check. One is it intuitively plausible? And the other thing is, does it match the data? Both of these things are not checked usually. So one of the things you can check empirically. You can look at the data and see if it looks IID. But the other thing, is it intuitively plausible? That's just as important, but it is not. It's not in the data. There is something which is called. So basically, the reason that the panel data analysis works well is because there is some process, some financialization process for this particular case. We're looking at the ratio of money to GNP, and we think it's a global process, so it's working in the same way across countries. So what is happening in one country can tell us some information about what is happening in another country, in the sense that all of them are behaving in the similar way. When you look at, for example, infant mortality over from 1960 to 2000, you see that all countries decline, and roughly about the same rate. Also, somebody who starts out high also ends up high, but all countries have cut their infant mortality rate by 50% over this period. So there is some general process which is, you can understand that health innovations are taking place and they are getting diffused throughout the countries, and so because of this we are seeing less infant mortality all over the country. If you look at each country individually, if you look at Pakistan data, you see that from 1970 to 2010, infant mortality was cut in half. So you say, oh, Pakistan has done great. But you find that actually when you look at the percentile rank, find that it hasn't changed. So it means that Pakistan has been doing the same as all other countries, and its position with respect to other countries have not changed, even though it has improved. So the idea that there is a common process going on is supported by the data, and so that means that if there is for example, if you have a country for which there is no data available, then you can, or a little bit of data and a lot of missing data, then you can use the information in the other countries to interpolate that since other countries are doing like this and all countries seem to be following the same pattern, so we can interpolate on this basis. But so that's the favorable case for empirical Bayes. The unfavorable case is one which you can say is unobserved heterogeneity. So the different countries are really different. There is no match between them. The process by which for example, you can think of the electric supply in Pakistan and energy problems in Pakistan and energy problems in the USA. So there will be no comparison. So if we think that we can aggregate countries and find some information from one to help us in the other, this will not be true. So even though if the numbers look exactly the same, the numbers may look very similar, and you might think just by looking at the numbers that okay, there is a similar trend. So this is called unobserved heterogeneity. I mean, there is differences, heterogeneity is differences, but they are not there in the data. They are in the real world. So if there are those things, then your empirical Bayes analysis will not work, because it's based on the real similarities underneath the series. So we need to have a match on both the surface structure and on the underlying structure. And basically today's econometric methodology is what is called nominalist. There are two philosophies of science. There's one is nominalist. Nominalist means names only. So it means that you only need to look at appearances. You don't need to look at the reality behind the appearances. And so the realist philosophy says that no, the reality behind also matters. So what I'm saying, so conventional econometric methodology is nominalist. So you only need to look at the numbers. You only need to look at the process which generates the numbers, the real world process. I'm saying that no, both of those are important and equally important. And so your econometrician cannot just do a data analysis. He has to understand the real world which generates the data as well, which involves studying things which are qualitative, non-numerical. Alright, so if we start and we get a preliminary analysis and we see that, okay, the IID assumption is okay for this data, both on the level of simple observational checks that the means seem to be stable, the variance seems to be stable, fluctuations are happening in the same way that one would see in an IID series. So visually the data seems to be IID, and in the real world also we have interpretation of the data which suggests that the IID idea is correct. Then we can start a data analysis. So now the analysis works by first reducing the data to the mean and the sum of squared deviations from the mean. So the formulas are AI, which is the sum of all of the observations, and the SI, which is the sum of squared deviations from the average. And one more number which is often convenient is the sigma hat squared, which is just derived from the sum of squared deviations by dividing by t minus 1. Now, at this point I'm doing a first approximation analysis. Later on we'll do the more complicated analysis. So a first approximation, I'm going to assume that sigma hat squared is the same as sigma squared. So there is no uncertainty in the variances. That means that we will concentrate on how the mean is being estimated. Later on we'll take care of what happens when variances are unstable. But it's very important to understand this case because basically the intuition is very clear in this case, and if I consider fluctuating variances, then the framework becomes complicated and it becomes hard to follow the logic of what's going on. And this is really the most important thing. We have done huge numbers of mathematics and derivations, but ultimately what matters is understanding this intuitive interpretation which we are going to go through. I did it last time also, but basically, as I said, you throw a lot of mud at the students, so only a little bit stuck the first time. Now this time a second coat will help. So now when we have made the assumption that sigma hat squared and sigma squared are the same, then the SI doesn't matter. It becomes sort of known rather than random. So the only thing which matters is the average, is AI. Now the distribution of the averages is this one here. AI is normal with mean theta I and variance sigma squared divided by t. I have put in a ti because it doesn't matter. I mean, we can have any number of. This doesn't normally. You see, there's a balanced panel. A balanced panel is one in which all of the observations are observed at all points of time. But here we can have an unbalanced panel. Each country, we can have different time periods. We can have missing observations. We just average what is available because it's IID. So a few points missing in the middle doesn't matter. In a time series, things matter much more because the position of time is important, but under the IID assumption, the position in time, it doesn't matter. So if we have different number of observations in each country, it makes no difference for this analysis. So we have AI is theta I, normal with mean theta I, and variance sigma squared over ti, which means that the average is more precise than an individual observation, and the factor by which the variance goes down is t. If you look at it in terms of precision, then the precision goes up by a factor of t. So it adds. If one observation has precision p, then t observations represent t times p. So now in Bayesian estimation, we have to choose a suitable prior for each parameter. If we choose the wrong prior, it leads to very bad results. So we must choose a prior which matches the information which is being provided by the data. This is the key to the empirical Bayes method. And again, the Bayesians don't like this at all, because they think that the data should not be used in because the prior is before the data. But this is a philosophy, it doesn't really have much practical impact. And in fact, if you guess the prior before looking at the data, you can get very bad results. But there is another way to synthesize the Bayesian view with the empirical Bayes, and that is to do a two-stage analysis. If we use an uninformative prior on the hyperparameters, which is called a hierarchical case, then we get results quite similar to the empirical Bayes, and we can also stay with the Bayesian philosophy. Well, I'll discuss that later. It's more complicated. In fact, my goal for this course is that there are 3 chapters at the end of my book, 16, 17, and 18. These deal with empirical Bayes. And at this point, I have set up the framework so that we should be able to read the chapter 16. And then later on, I think 18 deals with the hierarchical Bayes. And so we can do all of that. And if we do that, you will know more about Bayesian estimation than most people. Okay, so under the right circumstances, we get gain from empirical Bayes, because empirical Bayes adds prior information of value. Actually, this is important to understand, that Bayes is not magic. Because actually in the early times, when this issue was being discussed, people thought that Bayes was magic, because there was a theorem which shows that regardless of prior, this is called the Stein estimation technique, which was very popular, and I learned it and I studied the mathematics of it and so on. It turns out to be a dead end. But at that time, there was a theorem that you can do this and you can get a benefit, you can get a gain over classical conventional frequentist procedures regardless of the prior. So even if you have a bad prior, you can do well. So it turns out that that is true. There are mathematical techniques you can use, difficult ones, and that's what the Stein estimation technique is. That's what I studied very carefully. So you can use these techniques and you can make gains without ever having any losses. So the techniques that we are studying all have losses. Losses in the sense that if our prior is good, it performs well. If it is bad, it performs poorly. Now, if you use the technique that I am proposing, if you look at the Stein technique, then it allows you to achieve gains without having any loss. But when you look more carefully, you find that the chance, basically the gains are concentrated over a small portion of the parameter space, and that small proportion corresponds to the prior. So if the prior, so basically what you see is that if the prior is correct, then you can make gains. If it is not correct, then the Stein technique protects you from making losses. But it's kind of like an insurance. So if the prior is correct, then you make a very small amount of gain, because most of the gain is sacrificed to protect you from making big losses on the other side. So overall it's sort of irrelevant. I mean, because when the prior is exactly right or very close to right, and it's usually a very small small subset of three-dimensional space, which is impossible to hit by chance almost. So you make a very small gain in some parts of the data set, and you are protected from making huge losses on others. But overall it makes no difference, so you can just ignore it and do, I mean, in the sense that if you don't have accurate prior information, you will not be making any gains. So you might as well, instead of doing something very complicated, do the simple conventional analysis. So this was understood very late, and actually still not understood by many people. And after I wrote my book in which I explained this, I think 10 years later there's a book on Stein estimation that was published, which still is working with the same illusion that you can make gains without making losses. So the genuine thing is that if you have genuine prior information, then impose it, and you can make a lot of gains. And there is a risk that if the prior information is wrong, then you will make a lot of loss. So you should only do it with good prior information. But basically that's also what the same lesson is, that from the Stein estimation, that if you don't have good prior information, your gains are trivial and you don't make any losses. But that doesn't matter, since you can do the same thing with conventional techniques. So if serious gains are only possible if you have serious prior information. So Bayes is not magic. Bayes is a way to utilize genuine prior information. And so here, if there is genuine relationship across countries, now basically the goal of this lecture and all subsequent lectures in this Bayesian is to understand what is this genuine prior information, and where does it come from, and how is it used to get a better estimation. Okay, so we understand that the countries are likely to be similar in their, in the sense that all are countries in this world, and they are all using monetary policy, and basically economies work in similar ways. So they should have similar coefficients, but it is unlikely that the mean, which is the average ratio, should be exactly the same in all countries. So the classical techniques have only two options. Either they are all different, in which case each country's data is used only for itself and there is no borrowing of strength from one country to another country, or they are all the same, in which case all of the data is applies to every single, and so then you have a massive borrowing of strength. I mean, from n points of data, t points of data for one country, you go to n times t parameters, n times t data points, and only one parameter. So there's a huge difference if all of the countries are exactly the same. So the Bayesian analysis offers you an in-between position, in which you have some similarity and you use the similarity, but you don't impose identicality. You don't impose the idea that all of the parameters are the same. And also you have some control. You can judge how similar the parameters are. And so we will do that. So here is the crucial assumption that each country has different coefficients. Here is the AI is normal with mean theta I and variance VI, I am going to call it. All of the countries have different variances, and the variances are known for the first approximation. So that's the data distribution. Now the key is the prior distribution, which is that theta I is normal with mean M and variance V. So this is what we have imposed as the commonality. This can also be called random coefficients. So you see, the tightest information is that all coefficients are the same. The loosest specification is all coefficients are completely different and no resemblance. That's complete heterogeneity. And then the intermediate case is that all of the coefficients are similar. They can come from a similar distribution, but they are not the same. So this is the intermediate case. Now, if V is close to 0, the variance to prior, that means that all of the theta are tightly concentrated around the mean. So this is very much like having the same coefficient. And if V is very large, then they are all different and there is no relation between them. And so that's very much like having different coefficients. And so the middle cases are the ones where we have similarity. And those are the ones in which you get the power from the Bayesian technique. Okay, so we look at the formula for the Bayesian estimator, and that's over here. Theta hat I B. This is the formula for the ith country mean, and the B is for the Bayesian, and the hat is for the estimator. And so this is a weighted average of the prior mean M and the data mean AI. So there are two. The conventional estimator of theta hat I is just AI, the average of the observed data. So that's what you get from standard frequentist technique. It's also what you get from the Bayesian analysis with uninformative priors. So the natural estimator for theta I without any prior information is AI. If you have prior information, then you take a weighted average. You multiply the AI by its precision, which is Ti times Pi. You multiply the prior mean by its precision, P, which is 1 over V, and then you divide by the sum of the weights, P plus Ti Pi. Now this is the key formula to understand, that this contains both of the possibilities as a special case. If the data information goes to infinity, the precision goes to infinity, then this will converge to AI. The prior will wash out. It will disappear because all of the weight will be going to the data. So this is the case where all of the countries are separate and there is no borrowing from across the countries. Now, if P on the other hand is large, the prior precision is large, if all of the data are all of the theta are concentrated in a small neighborhood around the prior mean M, then you will put a lot of weight on that prior mean. So actually then you will not use the country data so much, and you will use the other country data in order to estimate the mean, which is exactly what we do. If all the means are the same, then we use all of the data from all of the countries to estimate the mean. So this is sort of a balance between the two. It borrows from other countries as indicated by the variance of the theta I around the mean. So actually this is what empirical Bayes mean. Empirical Bayes looks at how much fluctuation there is in the theta I, and if the theta are very tightly concentrated, then it will say, okay, my prior is very strong, and I will impose that on the country, and I will use the information less about the particular country, and I will use the aggregate information more. Now, so one estimator is pooling estimator, in which all the data is pooled to give one common mean, and that happens when the prior precision goes to infinity. Then there is the common mean M which is used, and the other extreme is when you have no pooling at all, or everything is separate. But there is one crucial issue which is not mentioned so far, and that is that what is M and V? I mean, I'm just saying that for different values of M and V, we get these cases which are nice, but the central issue remains that what should we use for M and what should we use for V? If I use M in the standard Bayesian methodology as some prior specification, then this whole logic goes apart. This whole logic falls apart if I use M and V on the basis of prior information, without looking at the data. This logic works only when we are using empirical Bayes, because we allow the data to tell us what the M should be, and we allow the data to tell us what the V should be. If M is specified before, then M does not borrow any information from the data. So it's not the aggregate mean. But it is the empirical Bayes methodology which allows us to use the pooling properties. So now we study. So basically the question that we want to ask is, how do we get M and V? Some ways of choosing M and V produce good results, and they do lend themselves to the interpretation that I am making. Other ways do not. So now I'm going to study the empirical Bayes methodology to show how this leads to the interpretation that we want to get out of this. So basically, empirical Bayes is based on, you see, the structure that we have is that the AI relate to the theta, and the theta relates to the MV. So AI depends on theta, which is the parameter. The parameter depends on the prior, which depends on the hyperparameters M and V. So there is no direct relation between the data and the hyperparameters. Hyperparameters generate the parameters, parameters generate the data. Now the empirical Bayes is based on integrating out the parameters. It takes them out from the middle and creates a relation directly between the data and the hyperparameters. So once you have that, once the thetas are gone from the middle, you see you have a joint posterior distribution. You have a joint distribution of the x and the theta I depending on the parameters, because the standard Bayesian setup, you have a conditional distribution of data given parameters and a marginal distribution of parameters given the hyperparameters. So when you multiply them together, you get the joint distribution of the data and the parameters given the hyperparameters. And if you integrate out the parameters, then you have the distribution of the data depending only on the hyperparameters. From that, you can use the data to estimate the hyperparameters, and that's the crucial step in the empirical Bayes method. So here is the current setup. I have the conditional distribution of AI given theta I is normal with mean theta I and variance VI. VI is just 1 over Ti Pi, or sigma squared over T, sigma squared I over T. Then we have the marginal distribution of theta I, that is normal M and V. And now I want to get the marginal distribution of the AI, the average of the ith country time series. So as I already discussed last time, A is centered around theta I is centered around M. So if we take theta out from the middle, A will be centered around M. If you think of what is the relation between A and M, it's clear that A will be symmetric around M, because theta is symmetric around M and A is symmetric around theta. So if you take theta out to the middle, it follows very naturally. So the mean of AI is M, and the variance also is very natural. A has, if you fix theta I, then conditional on that, there is a variance of AI, which is VI. Theta I itself has a variance of V, so you just add the two variances to get the total variance of A, conditional on the prior, after taking out the theta. So it's VI plus V. So the marginal distribution of AI is normal with mean M and VI plus V. Now, what this leads to is a very interesting situation in the panel data setup, is that we have this prior normal M, VI and V. We don't have an IID data, but we have lots of countries, so we have lots of observations AI which have the common normal distribution. The parameters are not the same, but they are quite similar. And so we have only two parameters and we have a lot of data, so we can estimate these parameters. And that's really the crucial step in the Bayesian methodology, that we estimate these m and v. So now when we estimate the m, what will happen? M will be, suppose that the vi are all the same, to have some understanding. Then basically the m will be the weighted average of all of the, will be exactly not the weighted, the simple average of all of the observations AI. So this is actually exactly the pooling estimator. All of the data will be pooled together to give you a single mean m, and so now the m will be the pooled data estimator, which, so this happens because of the empirical Bayes. If I use some other way of method of estimating m, I might not get to this. So so one extreme, there are two polar extremes that I was talking about. One extreme is that we pool all the data into one and we have only one estimator. And now the prior mean is actually, in the empirical Bayes setup, is the pooled estimator, if the vi is the same. If the vi are not the same, then the m is even cleverer than the pooled estimator. It says that, yes, let's pool all the data, but instead of pooling it with equal weights, we should give more weight to the data which is more precise and less weight to the data which is less precise. So if different countries have different variances, some of them have less data, some of them have more data, so you should give more weight to the country which has more data. And that's exactly what the empirical Bayes method does. So it chooses a sensible way of estimating the mean, and I will also explain the way of estimating the variance. So now it turns out that you can't find estimation formula for m and v, but given one of them, you can estimate the other one. And if you do an iterative process, it always converges. So here is our estimate of the, so let's assume for the moment that the prior mean v is also known. In that case, the prior precision will be pi equals vi plus v inverse, 1 over vi plus v. So now this is your formula for m. M hat is the sum of the averages, the weighted average, where each average is multiplied by its precision, and then you divide by the sum of the precisions. There's a little proof you can do, which I was tempted to put in, but then I took out, because you can prove that this is the minimum variance estimator. But I just didn't want to distract you. And also it's an easy proof, so you can do it yourself. So here, if I know the prior mean variance, then I just take a weighted, precision weighted average of the data averages, and I get the common mean. So this common mean is the pooling estimator. It says that if we pool all the data and we have just one mean for all the data, this is the mean. But the Bayesian estimation is clever. Instead of taking each country to have a different mean, it's putting the common mean at one stage further away, so that it is not imposing equality of means. If you impose equality of means and it is not there, then you get a strong bias. You're tying up, you're imposing equality too tightly. So this Bayesian estimator doesn't impose equality tightly, it imposes similarity. That's why it is strong, a stronger assumption, because it matches much more realistically to the real world, and that's why it works. It's not magic. It works because it's reasonable. It's reasonable to think that the different countries are similar, but not reasonable to think that they are the same. So if they're not the same, then the classical methods don't allow you to borrow strength, but the Bayesian estimator allows you to use this prior information that they are similar but not the same. And that's what accounts for the superiority of the Bayesian method. Now, if I know m, I can estimate v. This is the other part. So knowing v, I can estimate m, but now let's work on the other. So what we do is we say, okay, I estimate my m hat, and now I pretend that this m hat is the true mean, and now I turn to the problem of how we estimate the v. So basically the variance of AI around M is its variance, so Vi plus V. So expected value of AI minus M squared is Vi plus V. So I now replace the M by M hat. This is now with reference to the the marginal distribution of AI. I am relating AI to the prior mean M, and I note that the distribution, that the deviation of AI from the prior mean M is the sum of the two deviations. Actually, I can calculate it out also. I can put in AI minus M equals AI minus theta I minus plus theta I minus M, and that will be two components, and you can do the calculation and you can show the cross term cancels, and so the sum of the squares, which is one square will be Vi, the variance of AI around theta, and the other term will be the variance of theta around M, so you will get Vi plus V. So now the average value of AI minus M, this is the expected value. This is what would happen if AI was random. Now AI is actually observed, so the meaning is that if I subtract Vi from AI minus M hat squared, this will be approximately equal to V, which is what we want to estimate.
So this is a deviation from the combined?
Yes. AI deviates from theta I deviates from M. So there are two deviations in here. One of those is Vi and the other one is V. So now I look at the difference between AI and the common mean, and I know that this is the sum of two parts. So I subtract the one part, which is Vi, which is coming from the variance around theta I, and that leaves me with the V, which is the variance of the prior. So AI minus M hat squared minus Vi is an estimator of V. And now I have not one, but I have, for each country I have these estimators. So I take the average of all of them to get a better estimator. And so my first possibility for estimating V is that V hat is the average of this sum. For I take A hat I minus M hat squared, AI minus M hat squared, and I subtract Vi for each country, and I take these numbers for all of the countries and I take the average, and that's my estimate for V, which is the prior mean. Now there is just one thing that's a little bit wrong with this, which is that this can come out negative, and V variances are never negative. So a slightly better estimator is this formula 2, which says that if this ever comes out negative, replace it by 0. So you take the max of 0 and the difference, the subtraction of Vi from AI minus M squared. And that's it. This gives us an iterative procedure to compute the empirical Bayes estimator. I put in any guess for V, I calculate M hat, and then once I know M, I can calculate the V hat plus, and then I have a new estimate for the variance. I go back and plug in to calculate a new mean, and I go back and forth until these converge. And there is a theorem which says that this will actually converge, and it's actually quite rapid. You don't need to use a computer, you can just do it by hand, iterate a couple of steps, and you will get to convergence.
This looks like mean square errors.
Yes.
In this combination.
Yes, the variance is the mean squared error. Variance is the squared error, and the average of that is the mean. So since we are working with variances, these are similar to mean squared error.
Mean square error, like mean square error, which is equal to Bayes plus variance in
Here we don't have the bias for because actually we are just estimating the variance. The variance is directly expected value of x minus its mean squared. I think this is just confused thinking. So it'll take a while for you to see what's going on. All right, so basically here we are estimating the prior M and V. The prior M comes out to be basically the group mean, adjusted for the possibility that different countries have different amounts of data or different variances. So if they have different variances, then the means, we pool all the countries' means, but we pool them according to their variances. So if a country has high variance, it gets low weight. If a country has low variance, it gets high weight. So that gives us the pooled mean. Then we look at the fluctuation of these countries' means around this common mean, and we use this to estimate the prior variance, which makes complete sense. If the countries are not varying very much around that mean, that means that the prior is very strong. It's very good prior, and actually the for example, we can get, and there are some cases, that the V comes out to be 0 because you take this truncation, and so sometimes, for example, AI minus M hat is always bigger than VI, always less than VI. This means that the AI, how much AI fluctuates from M hat is within its own standard deviation. So there is no deviation. If all of the theta I are the same, there would be no problem, because this much deviation is explained by the data variances alone. No need for prior variance. So in that case, we can say that this is the polar case where you can pool all the data and get to a common mean. And then all of the data, if the prior precision is infinite, then basically we will pool the data and we'll estimate the same mean for all of the countries. On the other hand, it can also be that there is a lot of fluctuation in the theta I. So that says that your prior is very weak. Your prior variance is very high, and so you should not impose the prior mean. And this Bayesian estimator automatically takes care of that. So if the theta i's are deviating very much, then the estimator will say that, okay, let each country be estimated by its own data. Don't use the other country's data because they are too dissimilar. The dissimilarity between the countries is being measured by the prior variance. So what that means is that if the country means are ranging over a large group, then your empirical Bayes estimator will not work very well, because the prior variance will be very large. So there are a couple of things you can do. Sometimes you can see in the data that there are different subgroups. Like if you're working with countries, there are high income countries and low income countries. They behave differently. And so you're getting a high variance because you're combining all of them. If you separate them into two subgroups which are reasonable, you will get low variance for each of those groups, and you can do estimation separately, because basically we're trying to match to the reality as well, not just the data. The other thing is that if the sample sizes are very large, then the empirical Bayes doesn't do us any good, because basically if you look at the formula, you have Ti, Pi is multiplying the data mean. So if T becomes large, then even if the prior is good, it gets overwhelmed by the data evidence, and that's as it should be. If a country has a lot of data on its own, then there's no need to borrow extra information from the outside. You just use the country information. So basically the Bayes estimator is using a very clever way of averaging between the overall group mean and the country mean. It looks at all of the factors which come into play to create the group mean, and then it assesses how much weight should be given to the group mean and how much weight should be given to the country data. And this is the cleverness of the Bayesian procedure, which gives it the extra power. Okay, so that's the theory, and now we will turn this into practice. So I'm going to go back to the money price data, but I'm going to now do the full analysis. I mean, instead of looking at a special case, we will try to do the... So let's go to the prices now, because we've been working with money. Oops, clean data. Oh, good, I have the clean data. I hope I have the clean data for the prices. I think I did this last time. Okay, so in the process of cleaning the data, what we do is we omit the countries which have blanks. So I did that for the money side, all of the, but I didn't do it for the prices. So I'm going to do that in front of you, because now this is your assignment, and I think that before I go on to this is a crucial unit of the course. So before I go on to this, I would like to see, I think the Monday there is no class, and you should review lectures among yourselves. Amna, you will arrange this. Wednesday I'll come back, and instead of making a lecture, what I would like to do is to see about 2 or 3 analyses, or maybe more, from the students on their own data sets, so that I can see that you have understood what's going on. Okay, so I'll copy this to a new sheet. Alright, so this is the price data. ये 2004 ही तक आया, अच्छा चलो, let it be, since this is just for illustration. And I wanted to do serious data analysis of this data too. Okay, so one of the annoying things is that about the WDI data set is that they have groups like the whole world and Europe and middle income countries, and if you want to do just countries, then you have to eliminate those. That takes a little while. That's what cleaning the data is, one part of the cleaning data. And the other part of cleaning the data comes from the problem that there's missing data. So one way to take care of missing data is to sort. When you sort the countries, then the missing data all comes out in one place, and then you can delete it. Otherwise you have to go row by row and delete, which is a painful process. Okay, so let's go up to 2004 only. I don't know why, but I'll let it be. Okay, so this is, I have highlighted all the data, and I am going to sort this. Custom sort by, I want to go fairly out, a little bit further out. Initially there is lots of missing data. I want to have at least about 20 points of data, so 84 is a good place, but let me be a little bit more greedy and go up to 81. क्या हुआ? वो तो है. Let me eliminate Brazil. Let me eliminate Uganda. Let me eliminate Ghana. Oops, that was wrong. I wanted to delete the whole row. Now for Gabon, we have the option that I can eliminate 2 years and keep it. So let me just leave it for the moment. We might do it later. Okay, you see now the thing is that at the bottom we have all of these countries which are all blanks, so I can eliminate them all at the same time. Now, actually the methodology we are using doesn't require a balanced panel. We can work with missing data also, but it does require that these be IID. So now, are these IID? It's almost obvious that they are not. I mean, you can see that the index is starting at 18 and it's going up. And this is the price index, so we expect that this will be happening, that the prices will be increasing. So, as I said, the thing is to search where will our IID normal be, find a transformation. So as I said, the most common transformation here is to look at the rate of inflation, which is basically to take the log log PT minus log PT minus 1. And I mean, you can also take first differences without taking the log. Log usually smooths things out. In fact, in this case, I think both will work. Argentina is starting out with the very, very low prices, and e to the minus 11. So it has had some sort of a hyperinflation in there in the middle, and so this is going to be causing us problems. All right, let's look at first, make the transformation. So there are so see. Gabon is also going to be a problem, so I can either eliminate or I can fill in the blanks by some suitable numbers. Let me just eliminate it for the moment. So I have 45 countries, and now what I'm going to do is just copy them. So I copied them onto line 50. I want to have an okay, so I've got the labels. Now I'm going to use the logs. Okay, now what I want to do is to go to here and say equals ln of f2 tha na, f2 f2, right, minus log e2. Okay, so the entry here is the log of 61 price index minus the log of 60 price index. So it's the growth rate in price. Okay, so it's 12% was the inflation rate. Now I can just copy this. Okay. मुझे याद नहीं रहा कि कहाँ तक जाना है. Oops, अभी तक नहीं हुआ. So we are at 98. 2004 is only a little bit further away. $99. Okay. Maybe नहीं हुआ. Okay. Yeah. We got. All right. So these are the logarithms of the. These are the growth rates, and you can see that Argentina has really huge numbers. This is 169, which means 169% inflation, which is 28%, 4%, and so on. All right. So now what I want to know is, are these numbers compatible with the idea that this is an IID series? So actually the numbers for Argentina are not, in the sense that we have these small number here. There's actually deflation. Acha. So we have negative numbers, and then there's this period of huge inflation, 300%. So Argentina is clearly not a typical country and is not going to be useful for us in this simple exercise. There are models which have built-in outliers, and so in those cases we can do analysis without removing outliers. But currently, the way we are working with normal distributions, we can't afford outliers, so I'm going to get rid of Argentina. Peru, actually all of these Latin American countries suffered from high inflation, 28, 45%, 200% here, 300% here. So that's another 400% here. Bolivia and Peru. I'm going to get rid of both of them for simplicity. There are ways to take care of these things and include them in the analysis, but right now we're just doing simple stuff. Actually, Turkey also had quite a strong inflation, hyperinflation in 70%. Yeah, this is the Turkey had controlled inflation 50%, 53, 72, 63, 58, 61, 61, 49, and basically they got it down into 10%. This was my student Erdem Bashti at the head of the central bank in Turkey. He brought inflation under control in Turkey. But I think we still have to get rid of him. Still an outlier for the other data.
So rebasing the issue is where
Rebasing?
base different CPI given वो इस पर से different rate एक नई बेस पे शायद CBI गिवन और पुरानी बेस पे उससे पूछना चाहिए.
एक ही बेस पे करना.
You see, it shouldn't matter. There will, if that's so, then there will be 1 year in which rebasing is done, and then it will be the same. Yani, in that year you might see a jump differences. Basically, what we are asking for is, are these numbers IID across time? Acha, there is another way to also work with this. We are thinking of countries as being IID, yani each time series as being IID. It's also possible to look at the cross section, and that would be a different analysis, and sometimes for some data sets that will be the better analysis. So let me think of doing that as well, and show you how that might be done. For some data sets that will be better. Instead of saying that the each country is a separate case and each country is an IID case, we can think of each time period as being a separate case, and each time period as being an IID observation. Alright, so let's have a look at this. I want to look at the mean of this series. This is from F51 to F90.
F90.
F90. Oh, अच्छा एवरेज ले रहा था सही. Alright, so now let's see what happens to this average. I can plot it. So these are the inflation rates. So what we see is that there is a period of low inflation in the first 10 years here. Its inflation is varying between 4% and 6%, and then from the 10th year onwards we have switched to a high inflation regime in which inflation rates varies between 10% and 18%, and stays high up until towards the end of the period. And then near the end it again goes back to the low inflation regime. So there are actually two different inflation regimes, and so following the same, there are many ways to handle this, but the simplest way is to just get rid of the data which is outside and analyze just one regime separately. And the simplest way to handle multiple regimes is to just separate them into. So we could separate the data into two different regimes, high inflation regime and a low inflation regime, and then analyze them separately by using the IID techniques. So I'm going to look at the high inflation regimes. So high inflation sort of starts at point 14. This is point 13. Point 13 is 12%. And now point 12 is 7%. So I think point 13 is the one at which we have switched to the high inflation. This is overall I'm looking at. So you see here we have a jump. This is 7%, and then suddenly it's 13%. So this was the year in which a change took place. Now you see, as you're doing data analysis, you're also learning things about the data. So 1972 was the time at which big inflation took place throughout the world. So now you see what happened in 1972. Well, there was Yom Kippur War, and in 1971 I think it took place, or maybe 72. What happened was that the US supported Israel. When the US supported Israel, then the Arab countries decided to embargo oil to the US. When they did that, the oil prices shot up, and the Arab countries also realized that the oil price is very cheap and we can get much higher prices, because the US, which was the dominant buyer of oil, had been manipulated the price to keep the price very much down, as is happening these days also. So then they formed these OPEC countries, and then they hiked the oil price by quite a lot. And when that happened, since because oil is essential energy input, all over the world inflation took place. So now, one thing that should be clearly understood is that there is a theory which says that all inflation is always due to money. This is wrong. We see it in the data.
So similarly, there was in 1979 also, like there was the Iran Revolution, which also caused oil crisis.
Well, have a look. Did it have an impact globally? This is the question that we can check. Now that I will plot this again. After some time, this also went down. You see, when you're graphing, then things become clear when things are in the same scale. So I'm going to now get rid of these columns where we go back to the normal inflation regime from 1997 onwards. And now I'm going to plot these numbers. Okay, so now this seems very random. There is no autocorrelation. Yani the next point, it's very erratic. The previous point doesn't control what's happening next. So the independence assumption is reasonable, and I think that there is no particular obvious problem with the IID. There is a sort of a declining trend towards the end, but it's too minor to be noticeable. So we can start this our analysis on this basis.
Here 0.18 to 0.1 period decline. Won't that be a problem?
Where is 0.18?
0.18 at the top.
कहाँ पे?
This is starting period.
Yeah, this is a bit high, but basically what you need to look at is what is what distribution is this coming from, and let's look at that. This is equal to, we're thinking of this as an normal. But these are all averages. So 14.3% is the mean of this data set. And let's look at the SDEV. (0.2). So 18 is within 2 standard deviations of your mean, so it's not going to be an outlier, so it's not going to cause problems in the data analysis. Alright, now, so overall the mean is not drifting. That doesn't mean that each country is behaving well. It's this Uruguay is clearly a outlier here. It's another Latin American country. We might be able to actually do a separate model for Latin America. Alright, so now the first step to follow our analysis in the same way is to take the averages of these. We could also do it the other way, do the cross-sectional analysis, and maybe it's better for me to do that because okay, so let me try to do the cross-sectional analysis. Alright, let's do it that way. So now we're going to treat the time period as an IID period, and watch what happens to this pattern of inflation as time changes. So this is going to be F and a C 51 to C 90. अच्छा बीच में हमने किसी एलिमिनेट नहीं किया. All right, so that's 0.10. Now, now what I want to do is to see are there any outliers in the countries. So one way to do that, you can visually check also, but alright, yeah, I know how to do that easily. Equals max what's this, C51 to C90 equals min C51 to C90. Now, the maximum here is 67%, and basically I want to check if these countries are within 2 standard deviations. So I have 13% is the mean and 10% is the standard error. So 13 plus 10 plus 10 is 13, 23, 33. So 67 is a huge outlier. So that's not going to work with my IID analysis. So I should eliminate the 67. Uruguay. Now let's see what happened. The maximum is now 22%. Everything changed. 11% became the mean because the mean is itself sensitive. And notice that the variance came down to 0.5%. This is very important. Your basically the outliers spoil everything, the mean and the variance especially. So even one outlier in your empirical Bayes analysis will completely destroy the analysis, in the sense that suppose that all of the countries are falling into one pattern, but there's one outlier. So if that one outlier, your prior variance will be very high, because the prior variance is trying to match the data. So in order to see such a large observation, your prior variance has to be very large. So to fit the one outlier, the variance will become very large, even though most of the data has very small variance. So when the prior variance becomes very large, then the prior becomes irrelevant because the weight is all put on the data. So identifying outliers before doing this analysis is very important. So here we have 22. This falls. Now, does this fall? Actually, it would have fallen if we had 10% variance, but now we have only 5% standard error. But still, it's 11.5 plus 10 would be 21.5. This is slightly above 2 standard errors. That's not a big deal. So we can leave that be. And similarly, the lower side is also okay. Now I'm going to copy this. And now I need to check all of these things to see if there are any further outliers. Yeah, 77, 60. These are big outliers. This is 13% and 10%. 13, 23, 33, 57 is huge. Again, this 83% is huge. This 40% is huge. This 40%, maybe they are all from the same country, so let's have a look. Where is the 40? If they are from different countries, then we'll... Okay, here's 40. This is 40. Iceland. I didn't know that Iceland was having inflation problems. Okay, so let's go systematically. 33, 17 plus 12 is 29. This is a bit outside of bounds. Yes, let's take it out. Where is 33? This is, of course, the simplest form of analysis. As I said, Israel. Yeah, Israel is a hyperinflation country. We should take it out. Okay. So when you take out the country, then everything changes. So now you have 17 and 5. 17 plus 10 is 27, and now it's a little bit over 2, but I'll let it be. So we can get on with the analysis. Although it's true that the analysis will work better if there are no outliers. 13 and 12 is 25. 29 is still a bit high. Let's try for, where are these?
Sir, I read somewhere that if standard deviation or mean ratio is less than 30%, then there is no outlier.
क्या हुआ?
मैंने यहाँ कुछ चीज़ कहीं पढ़ी है कि अगर स्टैंडर्ड डेविएशन और मीन रेशियो लें और वो रेशियो 30% पे था तो इसका मतलब उस सीरीज में कोई प्रॉब्लम नहीं है, वो कंसिस्टेंट है. अगर ये रेशियो 30% से अबव हो तो उस केस में आपकी सीरीज में कंसिस्टेंसी नहीं होगी.
I don't know that rule, and I don't know where it could come from. Here we have 29% in Philippines, which is over, and there's, I was trying to see if there's same, but it doesn't seem to be. We can leave a few outliers in that they don't matter, but too many of them cause problems. As long as they're not extreme. One extreme outlier can destroy the whole analysis, but if ये नाइजीरिया का है, नाइजीरिया का भी प्रॉब्लम है और फिलीपींस का भी प्रॉब्लम्स है. Alright, so what I'm going to do, ये 54% आ गया, 24. क्या हुआ?
Last column में सर 84.
ये 84 है. This is very far out of the bounds of ये एक.
सर ऊपर ही बोला.
Sudan, acha. Okay, so I think we are out of time. So I will stop here. The rest of the steps you know how to do already. This is the second time around. So, and also I've given you the formulas. So, but the first part is important. I mean, you can't blindly apply data analysis to data. First, you have to study the data and make sure that the methods you are using are compatible. And this part is not done in most. I mean, if you take the standard thesis, they will never look at the data and they will run a regression, and it can have very disastrous consequences.
एक चीज और इसमें कर सकते हैं कि जो जो क्लस्टर टाइप है कि एक क्लस्टर को अलग से आप मॉडल कर लें दूसरे को अलग
Exactly. This is possible. You can take all of the Latin American countries and put them into one cluster. You can take all the similar inflation countries and put them into one cluster. Instead of eliminating outliers, I could look for the central group. I could take the median inflation and then say, okay, let me look at 10 countries above and 10 countries below. That will automatically give me a small cluster, which is okay.